So for part D of this one, we're supposed to determine the maximum compression of the spring. So basically, how far will it have been compressed from its initial length when the block comes to rest for a moment and then starts to go back up. So in order to figure that out, we need to use conservation of energy. And so because when the block starts up here, when it very first starts and it's released, it's at rest and the spring hasn't been compressed yet. So it doesn't have any kinetic energy. It doesn't have any elastic potential energy. So initially when it's up here, it only has gravitational potential energy. Then later, if you think about, so it falls, it hits the spring, and it's going to compress it to some maximum value. And that's what we're supposed to be finding here. When it gets to like its maximum compression at that point, it has come to rest momentarily. And so it doesn't have any kinetic energy again. And so all of that gravitational potential energy that it had up here, all of that loss of gravitational potential has now been converted into elastic potential. And so really we can just say the amount of gravitational potential it loses is going to be equal to its gain in elastic potential at that point, because at both of these moments the block is not moving and it doesn't have any kinetic, and so we can just leave kinetic energy out of it, which makes it simpler. So that's what I'm going to do. I'm going to say its loss of gravitational potential energy is going to be equal to its gain of elastic potential energy from the spring. So the loss of gravitational potential would be equal to its mass times g times its change in height. Now, its change in height, though, okay, if we think about this, a lot of you at this point just used 0.45 as the change in height, but it's falling all the way down to here, to where the spring is at its maximum compression. So that's not its total change in height. Like, as it's compressing the spring, gravity is continuing to do work on it and give it energy, because gravity is still a force acting on it even while it's compressing the spring. So our total change in height is going to be delta y, the amount it compresses the spring, plus the 0.45 that it fell initially before it hit the spring. That's our total change in height. So that will be our loss of gravitational potential. And then that has to be equal to the gain of elastic potential. And elastic potential is 1/2 kx squared, or in this case, delta y squared, because that x in that equation is the amount the spring is compressed or stretched from equilibrium. So that's our delta y squared. And there we don't include the plus 0.45 because it wasn't compressing the spring at that point. It was just falling. Okay, so this is our setup. And then you have to solve that. You plug in values for everything you know, which is everything except for delta y. That's your variable you're solving for. You get a quadratic equation, and you can solve it then with the quadratic formula, or you can use your calculator to solve it and give your solution.